So let me start our today's Kharkiv quantum seminar. It's a great pleasure for me to introduce our today's speaker, Professor Jukka Pekola from Aalto University, with his talk, Quantum Thermodynamics in Superconducting Circuits, Interference and Thermalization. Before he starts, let me introduce him with my one slide, with me showing one slide biography. In 1982, Jukka Pekola completed his Master's Science degree at the Helsinki University of Technology. Now it is named after Alvar Aalto, so it's Aalto University. In 1984, Jukka gained his doctorate with a thesis on critical flow and persistent current experiments in superfluid helium-3. He continued his work on the superfluids with a postdoc in the University of California in Berkeley. Then it followed by a return to Helsinki University of Technology to a position of group leader in the low temperature laboratory. In 1992, Professor Pekola moved to the University of Jyväskylä, co-founding the first nanophysics laboratory in Finland. Then he returned to Helsinki in 10 years, where he is now a full professor of quantum nanophysics at Aalto University. There he founded the PICO research group in the low temperature laboratory, which he heads to this day. Besides, he currently heads the Center of Excellence in Quantum Technology by Research Council of Finland and the Finnish Quantum Institute. In 2001, Professor Pekola was elected to the Finnish Academy of Science and Letters and to the Finnish Academy of Technical Sciences. He was awarded the Simon Memorial Prize in 2020 and the Magnus Ehrnrooth Prize by the Finnish Academy of Science and Letters this year. Of course, I somewhat shortened, but with this, I would like to give the floor to Professor Pekola, and hopefully we will learn how thermodynamics can be quantum.
Can you see now?
Yes.
Yeah, so thank you very much. Thank you very much, Sergey, for the introduction. It's a pleasure to give the talk today. So I'm going to tell about quantum thermodynamics in circuits, and especially I pay attention to some features which are let's say purely quantum, and quantum thermodynamics of course means very different things for different people. So I take a few minutes just to introduce what I mean by that. So okay, see. So let's start with a cartoon here. So we are usually, what we are looking at is a system in a circuit, which can be in the simplest case, it can be just a superconducting qubit. And this superconducting qubit is naturally, coupled to different environments, heat baths and whatever non-equilibrium environments. So what actually I mean by quantum thermodynamics is the open quantum system physics in these circuits, and especially to study their thermal properties based on the known open system methods usually. And there are kind of two different opportunities, or two different viewpoints of these studies. One is to try to look at the system itself as it talks to the environment, or try to get information about the dynamics by looking at the environment, which is usually considered to be a formidable, difficult task. But as I will show, our environments are usually somehow controllable, and also they can be made mesoscopic, such that the properties are reacting to the changes in the actual quantum system, and this way we can get a handle to look at these things. So let me first start by telling a few words about just what are kind of the phenomena that we are interested in, and what I'm going to present in this talk. So if you're talking about quantum features, then naturally quantum interferences, which actually relates very closely to what has been studied by our chairman. Now we have a possibility to study that in properties of energy exchange, the heat exchange, and this is one of the topics that I will tell to you today. Another topic that is also mentioned in the title is the thermalization of an isolated quantum system, which is a long story, of course. Theoretically, it has been studied for quite some time, starting from God knows when, and it has been also, there have been different approaches to this problem. There are very few experiments on that, but in today's talk, I will give you kind of a blueprint of how one can study these things experimentally. Then there is another interesting possibility is that one can get in these systems, as I said, since the environments are usually mesoscopic, one can come to the limit where it's, at least in principle, it's possible to detect single microwave quanta. So the photons emitted by single qubits, for instance, or resonators, and this is something that I will also tell you briefly about. And then, of course, there are many other things that are of interest in these systems. But it's not only about phenomena; it's also about devices and applications in some sense. So what I will tell you today about is that one can make, using these techniques, one can make bolometers, very sensitive detectors, which can be used as thermal spectrometers. Also related to the single photon emission and detection, we can make colorimeters, which are ideally can resolve a single photon. Then there are quantum heat engines and refrigerators. I'm not going to say except just a few words about this today. And then what I'm also going to tell is the thermometers that you can make out of just a simple qubit. So this is quite a collection of things which all connect to each other. And besides this, there are, of course, many other things that one can, what we have addressed, which I will not touch at all today. For example, Maxwell's demons, refrigerators operating with thermal noise, or thermal rectifiers or diodes. So this is kind of the ballpark where we are working in this, and we are doing mainly experiments, but also some theoretical works on this. So let's go now to the actual thing. So let's start from this more traditional way, although something that is probably initially thought to be the difficult way to look at the environment when it's coupled to a system. So what this leads to is, or what this means is that you need to have a well-defined, one could even say an engineered environment. You can have like in the simplest case, you can have a metallic resistor like this one here, whose size is about a few microns. This is probably 2 microns long here, and this means that it has a large number of electrons, of the order of billions of electrons in it, and they in equilibrium they form naturally a Fermi-Dirac distribution, which tells us what the temperature of this resistor is. And the way to detect these temperatures is to connect some sort of tunnel contacts there, which I will show to you in the next slide. So when this kind of a resistor is exposed to different sources of excitations, for example, it can be exposed to the external radiation, it is coupled to the phonon bath, or it is coupled to the other electrical leads here, then the distribution here is influenced by these disturbances. So, but the good thing usually is that electrons in a metal, they talk to each other quite fast. So there's an electron relaxation time, or the relaxation time, which is typically of the order of nanoseconds in this low, let's say, sub 100 millikelvin temperatures that we operate these things at, whereas the couplings to the external world are usually much slower, for instance, to the phonons. So it means that we usually have a well-defined temperature in these things, and therefore we can call them as heat baths. But the good thing is that since it is weakly coupled to this kind of a super bath here, then by its temperature, the local temperature of electrons can be controlled by external means, for example, by Joule heating. So what is the simplest thermometer? The simplest thermometer that we use, kind of bread and butter for us, is a tunnel junction between a normal metal and a superconductor. So this NIS refers to normal insulator superconductor. It's made by very standard lithographic means, similarly to Josephson junctions, but now with a normal metal, which is typically copper, or it can be chromium, or it can be whatever normal metal. And the thing is that the current through this kind of a junction is given by this type of a Landauer type of a expression, where you have the density of states in the superconducting lead, which is essentially temperature independent at low enough temperatures, and then the distribution of electrons in this normal metal. So, in fact, it's only measuring the temperature of the normal metal. And if you actually do the math here, you find that at temperatures well below the superconducting transition temperature, the current depends exponentially on inverse temperature, like here. So you can bias it at some certain point, and you can see that if you, for instance, measure the current voltage characteristics at different temperatures, you see that there is a slope here, which is, in fact, it is just giving the temperature in a primary way. So this is the thing that we usually use. So in simplest case, we apply a current, which is a constant current, and we measure the voltage here, and then this tells us the temperature of the normal conductor that we are looking at. So what we mean by bolometry is that if there is an external heat load, heat flux into this kind of a resistor, as I showed, then due to the thermal resistance between this absorber here and the big bath, which is usually formed by the phonons, there is a temperature difference between these two, and this is like like Ohm's law type of a expression naturally. So the temperature rise here is proportional to this heat flux that is entering here. So by measuring the temperature here, one can tell how much energy is exchanged with the external world. And this is kind of a DC steady state measurement in most of the cases, but I will come to some fast measurements later on in the talk. So let's now focus on these bolometric measurements that we are doing routinely. So they can be applied to various different things. So I just show here a collection of many things. I will not go into detail of all of them, but in general, always there is the case that you have this kind of absorber, which then is the detector of energy currents. What I'm going to talk quite a lot today about is this kind of a setup where one can probe and characterize superconducting circuits, quantum circuits, and resonators by just measuring the leakage of photons to this kind of a bolometer and measuring the temperature differences. But let's start from something rather archetypal and some experiment that we did a couple of years ago, just to give you the idea how this can be realized in practice. So of course, a kind of a basic experiment is that you have two different heat baths, let's say hot and cold bath, and you put in between some quantum object that then of course influences the transport of energy, transport of heat between the two baths. And in this case we realized it as is shown here below. So we had a superconducting transmon qubit here, xmon qubit here, whose energy is tunable by magnetic flux here. There's a squid in this qubit, and then it is connected to two coplanar wave resonators. In this case, they were of equal frequency, and they were capacitively coupled to this transmon qubit. So there's no galvanic connection between the resonators and the qubit. Moreover, at the two ends, we have these baths, which look pretty tiny, but they are the things that really matter in this case. So these baths are indeed, they are like 3 micrometers long, in this case, resistors, whose temperature we can joule heating control, and also measure by these tunnel junctions. So that's very simple experiment is then that one increases the temperature of one of the resistors and then measures what is going on the other side. And the cartoon telling what is going on is shown here. So when we are changing the magnetic flux to change the inductance, changing the energy of this qubit here, then at some point this qubit becomes resonant with these two coplanar wave resonators here, and then it admits the photons to propagate from the hot bath to the cold bath, which then leads to the increase of temperature of the cold bath. And this is what we could see in those early experiments. So what we did was that we had two different regimes actually. So there are like two important couplings. There is a coupling between the qubit and the resonator, which we call here G, which is a symmetric structure, and then there is a coupling between the resonator and the bath, which we call gamma here, and this gamma here is essentially the same as the quality factor of the resonator. And both these things can be tuned by choice of the geometry and the resistance of the bath. So in this first case, when this coupling between the resonator and reservoir is strong enough as compared to this coupling here, we can consider that the qubit is coupled to a kind of a structured environment. So there is a Lorentzian filter here between the qubit and the reservoir. And this leads to the power, which we can determine from measuring the temperature rise here. So the temperature is not shown directly here, but it's just converted already to the power via this this ohmic dependence between the two. And you can see that when we change the magnetic flux so that the qubit comes periodically twice in each period resonant with the resonators, you can see there's a maximum heat current between the two. And this can be done at different bath temperatures, and one can even do so that you cool this, because there's also a possibility to cool one of the reservoirs, and you can invert this heat flux between the two baths. So this is kind of basic configuration. Perhaps a little bit even more interesting case is that you can change the hierarchy of these couplings. So you can say that, let's say that this coupling between the qubit and the resonators is stronger than the coupling to the baths. All of these couplings are quite weak here, only of the order of 1% or so. But anyway, so you can invert this by changing the resistance here and changing the geometry of the coupling here. In this case, the thing becomes, the system becomes like a hybrid, where you have the qubit and resonator system as the quantum system, which is then coupled to bare heat bath. And we could model this. I mean, experimentally, the flux modulation pattern is different from the earlier case, and we could also model that by just diagonalizing this simple Hamiltonian here and coupling it to the bare heat bath as shown here. So this was the basic experiment. Another thing is that one can use this actually quite in an interesting way, this bolometric detection. We are doing a DC measurement of temperature here, but we can address the AC properties of the system, because the power as such is quadratic in currents there. So for instance, if you apply a voltage bias across a Josephson junction, it starts to naturally it starts to emit photons to the environment at the frequency, Josephson frequency, and then what you can do is you can try to see whether this is seen as the power increase in these bolometers, which we in this particular case we set 2 bolometers at the equal distance on the 2 sides. And the actual design of the system is shown here on the chip. So it's again a structure with about tens of micrometers long, and here is the central Josephson junction. So the idea is that when the junction is biased, it's running down the ladder in, let's say, the washport potential, and at each drop here, it is emitting a photon, which is then in this case detected by this resistor here. And indeed, this is what is happening. So this is kind of a very sensitive detector of this thing. So if we measure the temperatures of these 2 resistors here, while we give a voltage bias to this junction, we can see at different bath temperatures, starting from 40 millikelvin up to a few hundred millikelvin, we can see that there's quite an interesting pattern of how this temperature at different bias voltages is behaving. And this, in fact, these different regimes here are given by are such that in this range, where you are still in the subgap current range here, you have the maximum power which is carried by these photons. Whereas when you go to this range of quasi-particles here, then the power is just diffusing through the leads, and the temperature increase is much weaker. Nevertheless, it was quite remarkable that in such an experiment we can first of all model it as just an emitter of Josephson radiation, where the phase is running at the frequency given by this biasing voltage, and if you then convert this to the power that it is burning in these absorber resistors here, you can see that a very simple expression catches up this power that we measure at sub-gap voltages. What this measurement tells is that since we can measure this up to about 200 microvolts here, it tells that such a bolometer is capable of measuring power at frequencies up to about 100 gigahertz, which is kind of a new regime for doing power measurements, or in fact measuring even in general. So this led us to go to look at the properties of this kind of a bolometer as a thermal spectrometer. So let us see that now. Let's take a simplest possible system. So let's take this kind of a coplanar wave resonator, which is then coupled to this bolometer, which is here capacitively as before. So this is kind of the equivalent circuit of the system. So there's a superconducting resonator is capacitively coupled with a small gap there to this bolometer here. Now we can drive this resonator by this drive line or this feed line here, which is coupled either capacitively or inductively to this resonator here. So now one can model this system by different means. You can do a simple, since it's a linear circuit, you can do just a circuit theory and find how much power are you expecting to observe here in this bolometer here. or just having in mind that we can do it also for nonlinear circuits, you can also think that you have a driven open quantum system. So in this case, it's just a kind of just a simple harmonic oscillator. But when you drive it, it tends to be excited, but then it couples to various paths that it is, whatever path it is coupled, plus to the absorber, which is kind of an artificial absorber, artificial bath whose temperature we are monitoring. And the nice thing here was that when we are doing this, we can see that if we measure the temperature by this very same thermometer here, we can see that the thermometer is reacting in a Lorentzian way at the resonant frequency of this resonator, which in this case happened to be about 7 gigahertz. And this change in temperature, which is actually only thermal voltage here, is in more or less proportional to the power here. And if you contrast this to the conventional way of measuring a similar or exactly the same resonator with a conventional means, where one uses the microwave driving and measuring via the chain of circulators and amplifiers and vector network analyzer, we can see in this case much more clear resonance, because this is not affected by the background, which is coming from the mismatch in the lines here in general. And also there's another important feature of this, that this particular technique can be also applied at higher frequencies. I told that we can go even up to 100 gigahertz. So here we went up to 20 gigahertz. So we could see that this thermal spectrometer can see also the energy of the second harmonic of this resonator at 20 gigahertz, which is not achievable by the usual spectroscopy, which is used in usual qubit measurements. And here also one can see that one can also see powers which corresponds to one average photon in this resonator, so that sensitivity is also quite good. But let's go a little bit more to the physics now. So we will go to these interferences. So I think at least to part of the audience here, I don't have to tell much about Landau-Zener-Stückelberg interference, because the real experts are there in the audience. But nevertheless, this is something that has been studied experimentally in the superconducting circuits already for quite some time, just by measuring essentially the microwave reflection, microwave transmission in a system. So there's an experiment by Will Oliver, 2005, where driving periodically across an avoided crossing, one could see that there are these periodic features in the system. And also there's an experiment here at Aalto University around the same time with a single Cooper box, where also this Landau-Zener, periodic Landau-Zener was observed in these interferences that's shown here. So now I want to advertise here our common work with Sergei Shevchenko and Oleg Ivanenko, with whom we were looking at exactly the type of the system that I was just showing, yet without this bolometer. So this is the only data that I show where we didn't actually measure the thermal properties of the system. So what we did was that we took a qubit, and in this case a flux qubit is shown here, which was strongly coupled. The key point here is that this is a strongly coupled system coupled to this coplanar wave resonator here. It's done by a galvanic coupling, so that we can get to the couplings which are of the order of 10% or even above 10% of the resonance frequency of the resonator. So this is kind of in the strong coupling regime. And then if we drive the qubit, one can look at the corresponding interferences by measuring measuring the probe line here, which is weakly coupled to this resonator. And one can see very interesting resonance features depending on the flux biasing of this qubit, so the DC flux biasing, and then the amplitude of the AC drive of the system here. So here is what we observed in the experiment, and this. I'm not sure if this is our latest theoretical plot, but it's calculated by Oleg and Sergei and Franco Nori. So this shows the corresponding pattern with the same parameters done with the master equation simulations. So there is a reasonable correspondence, but of course some of the parameters in the system are not precisely known, and that makes it still. The full quantitative fit is not quite perfect yet. But let's now go to the thermal measurement of the corresponding phenomena. So it's not that much new physics beyond this strongly coupled, strongly driven system. But now what we are doing is that we are using a thermal probe here, and this has something which is our interest in here is that we want to make heat engines, or let's say refrigerators, out of this. So therefore, having this thermal setup is interesting beyond the fact that we can now also just for the sake that we can measure them by thermal means, this quantum phenomena of this system. So here is the experimental setup, which is I don't go into the details. It's exactly, there's a flux qubit, there's a resonator, and then there is this on-chip thermal bath that we measure. It has the standard spectroscopic features. So there's the resonance at 7 gigahertz. There's avoided crossing there, so forth and so on. So now what we can do is we can drive this system by AC at the desired position in flux here, DC position, and then different amplitudes of the drive, and then we can monitor the temperature of the bath here. So there are some interesting expectations about this heat, and one of them is that there is a, when you drive this system, then there is a dynamic phase of the system, which you can even model it by the simple master equation. You will see that if you drive the system, then there will be resonances in power into this bath, which are at fractions of the frequency of this let's say in this case, if it's just a qubit, then it is just the average energy of this qubit. Or if it is coupled by a resonator, they are fractions of this resonator frequency here. And that's simple to understand because there is an accumulation of phase here, which is given by this simple expression. And this naturally will have a lot of influence on how, for instance, these heat engines and refrigerators would behave at high frequencies, which is shown here. So we have, some years ago, we have proposed a kind of, as one example, a quantum auto refrigerator where one can drive, for instance, a flux qubit, which is sandwiched between two resonators, which is just shown here as like this kind of bulk, let's say the lumped resonators, where they have different frequencies. And then when you do a cyclic drive of this qubit frequency here, you can carry photons from one bath to the other. And ideally, this is, if you are in a quasi-static frequency range, then the power that you carry from cold bath to the hot bath is proportional to frequency. But as soon as you come to this regime where there start to be quantum interferences, you start to have, in fact, a negative impact from these frequencies. So it's there's a true influence of the quantum effects on this of this device, which actually unfortunately is not positive for this case, but it is interesting anyways. So what we did in the experiment was that we were driving the qubit. Now, as I said, and we were measuring the DC temperature of this single bath. So this is not yet the auto refrigerator because we have a single bath and there's a drive and there's a single bath. And what we did see indeed is that keeping a constant amplitude of this drive and changing the frequency, we can see that if we are sitting exactly at this symmetry point of this qubit on the average, then we can see that there are only the odd frequencies of there's a 1/3 of the frequency of the resonator, there's a 1/5, 7th, 9th, 11th, so on, which are visible in this measurement. If we just detune it slightly bit from the resonance, what happens is that we start to see also the even frequencies in this very same measurement. So there's kind of a selection rules which are controlling this phenomenon of having these fractional frequencies in power. And when we did a two-dimensional experiment on this power that we measure at different frequencies, so here's, for example, 1/3 of the resonator frequency, and here's 1/4, we can see that there are indeed this pattern is quite well reproduced by Floquet theory that we have now developed for this system. And indeed, at this even fraction, there's no power whatsoever at the symmetry point of the system. One can do much more. I will not go into details here. So you can see that this really applies to the same. This systematics is really robust in the sense that you can look at different fractions and you can see that indeed, as a function of the flux and amplitude of the drive, there are these features which we predicted. So to finish this part, then there's also a possibility really to use this now as a spectroscopic technique to measure qubits at higher frequencies than what has been possible up to now. So we just demonstrated here where we have been driving the with a feed line, we have been driving this system, this strongly coupled system here, and we can see that there are this whole spectroscopy of the qubit can be seen both around the basic harmonic frequency of this resonator, but also at this next harmonic, which is 3 times the basic frequency. And there are some new features which we still don't even understand in this system. Okay, so let's make a small detour about what is our interest in. Another interest here is trying to measure the tiniest possible heat currents, and there are some limits in thermal sensing which nature gives us naturally. So what is for instance one of the things is that energy resolution of a calorimeter is limited simply by this expression where we have let's say we have a calorimeter which is living in surrounded by a bath at temperature T0 here, or T, and then naturally it's exchanging whatever excitations with this equilibrium environment, which tells us that there will be fluctuations in the energy of this absorber, which then translates to the fluctuations of the temperature, effective temperature of this absorber. And ultimately, if one has an ideal thermometer, then this energy resolution here is given by this expression. So it's the heat capacity times the temperature. It's square root of heat capacity times the temperature. So in order to have a good resolution in temperature, in energy, one should go to very low temperatures and also to have very small heat capacities. This is all very easy to see from just the fluctuation dissipation theorem. You can for heat currents, you can find out that, for instance, the temperature fluctuations of temperature are given by kT squared over C, which is known from the textbooks. So this sets some limits to how good a thermal detector you can make. So, but there are several different options how one can address this. So I have been talking a lot about these usual normal metals where we have these standard thermometers. This is a good absorber for aiming for this at low temperatures, because it decouples from the bath, the phonon bath, like with high power or temperature. So there's like a T⁴ coupling to the decoupling from the bath, and then it's easy to adapt these thermometers to it. There's another option is to use semiconducting wires, which people also are using, for example, in Lund in Sweden. So one can have low heat capacities, but decoupling from the phonons is not quite as effective as with metals, and the thermometry is not quite as straightforward. Then one can think about using graphene, and we have been working recently on epitaxial graphene, where a graphene sheet is which has a very small heat capacity, and one can do simple thermometry just by applying the small current. You can measure the in situ the resistance, or let's say conductance of this kind of a sheet. But it's also not fully decoupled from the phonons at low temperature. So my favorite one at the moment is to use a normal metal absorber, which is slightly proximatized by a superconductor. There are two different advantages that this would give in this kind of a detector, is that one could decouple it from the first of all, you can get decreased heat capacity, and also you can decouple it from the heat bath. And then we have developed a proximity thermometer for this, which is such that you have if you have this very same thermometer or junction as I explained earlier, but now you make a superconducting contact nearby it. It gives you a little bit of superconductivity in the region of this junction, which gives you a tiny little supercurrent. The advantage of this is that this supercurrent is extremely sensitive to temperature because it's small supercurrent, and also since you measure supercurrents at zero bias, it means that also the self-heating in this measurement is negligibly small. So we have developed this thermometer now, and we can use it down to about 20 millikelvin temperatures. And then another advantage is that you can also embed it into kind of a tank circuit, where you can measure it fast at the rates of the order of 1 microsecond, which is already in the range of the thermal time constants of the system. So one can also look at the temporal variations of temperature with this system. So we don't yet have any single photon detection, but what we have been able to show is that the noise that we see in temperature of this kind of an absorber is so low that it should be possible to, if we have an ideal thermometry, it should be possible to see the single microwave photons of 1 Kelvin, which is about 20 gigahertz, with a signal to noise ratio of about 10. So this is a direction that we are pushing, but don't have yet final results on it. So now I'm sorry, I have this some background noise here. So let's now go to for the rest of the time to the microscopes of the system itself. So when we have the open system which is coupled to this environment, but we are looking at the system itself. So first of all, I start by telling that in this case, let's take, for example, a qubit which is coupled to this bath. Its population, if everything is in equilibrium here, naturally population of this qubit in the excited state without any drive, without external disturbances, is given by this Boltzmann exponent here, so that depending on the energy and temperature, you have some population in the qubit. So this is kind of basically this is a nice probe of temperature of a bath, but qubit as such does not have temperature. It only has the population, and you can have whatever population, but only in equilibrium. Yeah, they have the population corresponds to the temperature of the bath that you are measuring. So what we did recently was that we set up an experiment where we apply different pulse sequences to this qubit to extract as effectively as possible the temperature of the heat bath here. And it was devised so that we apply 2 pi pulses to the qubit, such that after that, by reading out the signal here with a certain protocol developed in a group of Sorin Parauno here, we could then determine the effective temperature of the bath from the outcome of the measurement. So I just give you a main conclusions of this work. So what we found is that indeed our data, if we determine the effective temperature from this population measurement of the qubit, it does obey more or less. It follows more or less the temperature of your refrigerator in a certain temperature range here. At low temperatures, the reading saturates, and at high temperatures you get a lot of noise there, or let's say the reading becomes very unreliable. The low temperature part is determined by the fact that and this is something which is limiting most qubits, is that the system always couples to some unknown bath as well. So this is kind of not a very good case, but it illustrates this feature quite dramatically. So in fact, we can model this situation by assuming that the qubit is in fact coupled to the bath that you want to couple it to. That it means that the mixing chamber of your dilution refrigerator. But besides that, there is another bath which we don't actually know, and we don't need to know much about it. We only need to know what is the noise at the frequency of the qubit here, and we can make kind of a two bath model which tells us that the effective temperature is just of the qubit depends on the coupling and temperature of that extra bath here. And it gives us a saturation which is really hard to fight against, because even with very weak coupling and rather low external bath temperature, there is still saturation in few tenths of millikelvin, which is where qubits are these days inevitably sticking to. But at higher temperatures, there's also a difference in slope because of the coupling to these 2 baths as well. So this is indeed what happens, and we did measurements with somewhat better qubits and better environment, and we could see that we can go down to about 40 millikelvin, and this slope here becomes quite more or less like 1-to-1 as compared to the mixing chamber temperature. So this is a thermometer which is the smallest thermometer that you can imagine, and with very small heat capacity. But it is, on the other hand, it's a very susceptible gadget in terms of the external noise, like the qubits usually are. So let me now finish this by this talking a little bit about this thermalization. So there's a starting experiment on this. No results to report yet experimentally, but conceptually this is a quite interesting problem, naturally. So let us take any quantum system, let it be like a multi-level system or qubit or whatever, and when it's connected to the heat bath, then you of course expect that the populations on the different levels of this system are distributed according to the thermal populations. So the big question which people have been thinking, of course, is that what happens when the system is isolated, and does it still find kind of a thermal, when you first drive it into non-equilibrium, does it find a thermal population, and under what conditions? And this there are several reviews in the past decade on this topic, and there has been this theory of this eigenstate thermalization hypothesis-based theories on this problem. But now we kind of got interested to try. Yeah, there are very few experiments in this direction. Some with cold gases and cold atomic gases, but not very conclusive ones up to now. So what we are thinking is that the superconducting qubits and resonators nowadays they form almost isolated systems. We know that the first superconducting qubits about 25 years ago, their lifetimes were like in the nanosecond level, whereas these days we start to approach millisecond, and also the resonators have huge quality factors in the range of millions or higher. So they kind of, you can start to think that you can form experimentally systems where you have qubits coupled to other qubits or qubits coupled to resonators, which then form more or less isolated systems. So there are then, of course, a lot of questions there. What happens in this kind of a situation? And if you excite, for instance, a qubit, what happens to its population? What happens in its dynamics after that? And under what conditions? So this can be, of course, contrasted to what we already saw. So if you have a resistive bolometer coupled to a qubit, I forgot to put here experimental data which we have on this also. Well, if we excite the qubit, it's naturally its population in the excited state this is a standard kind of a T1 measurement of a qubit. It relaxes, the population relaxes over time, tau, which is the T1 time of a qubit, without any revivals, naturally, because we have a bath, even with this electronic resistor, we have a bath of billions of electrons, so it's really a many-body bath, which really is a swamp of energy of the qubit. But you can then think that, is it possible to have some sort of synthetic baths? And people are these days often claiming that Johnson junction arrays or waveguides or transmission lines, they also form heat baths, which is actually not true at all, because you in these cases you have inevitable revivals because of the resonances in the system. So this is a kind of a demonstration of such a setup where in Chicago in Andrew Cleland's laboratory they had a qubit coupled to a very long transmission line. So this was like almost 1 meter long superconducting line here. And now when one excites the qubit and measures its population after this excitation, forget about the other side of this because it was kind of shut off in this basic experiment. What they saw is that the qubit population, it really first drops, but naturally when the signal bounces back from the other end of the resonator, you get almost a full recovery of the population of the qubit. And this repeats periodically. Of course, there are some, it's not perfect, but still. And this can be, this is what we did with my postdoc recently. So we also simulated this by a very basic model, solving just a Schrödinger equation of this whole system without any environment here, and we can see that naturally that there are these recoveries happening at the time, but as in the experiment. But what is kind of interesting is that in the initial drop here, the population really drops by theoretically by many orders of magnitude before it recovers. So for a short time you could kind of consider it as a bath, but then you have these recoveries. So what is the way to get around this? And this is what we propose, and now we are kind of starting to experiment on it. So its a possibility is to make a multi-qubit bath. So suppose that indeed you have many qubits which are coupled to this central qubit here. Let's take just theoretically a case where we have initially all the qubits here are in the ground state, and except one of them is by a pi pulse excited to the excited state. And then we look at the population of this central qubit here. Just taking the simplest possible linear coupling between them, and with random couplings and sometimes random energies here. So now if all the energies of the environment qubits are the same as the central one, then what one can see is what you've shown here by the gray line. There's a perfect Poincare recoveries because it's kind of performing perfect coherent oscillations between the qubit and the rest of the qubits here. If these ones are detuned from the central qubit but have the same energy, then even then you can see that there are perfect recoveries, but with smaller amplitude. But if you give a wide distribution of energies of the environment qubits here, so here we had like 10 million qubits. So if you give a wide distribution of these energies, let's say from 0 to 2 times the central qubit population, then you can see that there is a really an exponential decay of this population. So this kind of system acts as a synthetic heat bath. So we were now asking a question, because we can't make 10 million qubits on a chip. We're asking a question, can we have a blueprint or an experiment where the number of qubits is somewhat smaller? And here is just time traces of the excited state population of the central qubit in the same type of experiment I proposed. So first you excite it, and then if there is just 1 qubit in the environment, then of course you have these oscillations. If you put more qubits, you start to get less regular oscillations and more damped oscillations. If you have 10 to 6 of them, or again with different energies, you have the decay. So now our kind of idea is based on what we did in this initial theoretical work, is to look at as a function of number of qubits in the environment, to look at this kind of a Poincare recovery time of the qubit when it comes to within the distance of delta from full recovery here. And setting this delta and looking at it with different numbers of qubits here, we can see that there's always this average ensemble average recovery time scales exponentially with a number of n, which is quite simple to actually show. And then this this increase here is so rapid that already with, let's say, a number of maybe a few tens of qubits, this time becomes of the order of age of the universe. So these times here are scaled by the inverse frequency of the qubit. So even with a few qubits, there's quite substantial recovery time which one can try to look at, and the numbers are really quite promising. So at the moment, what we are doing together with the group at the University of Chicago, we are looking at a system which they published last year, where they have a qubit coupled via router with tunable couplings to several other qubits, and one can do exactly the experiment that we were which I was just now discussing. So the idea is to look whether this sort of a synthetic heat bath can be formed even with a small number of qubits. So this is essentially all. So I will just tell here our group. So much of the work was done with Bayan Karimi, who is now in fact she was my student postdoc. Now she is a postdoc at the University of Chicago at the moment. Then these interference experiments were done also partly in collaboration with Sergei and Oleg, were done by Dimas Satria. And then the qubit thermometry experiments were done by Dmitry Wolf and Sergei Lemtyakov. And then Yucheng Chang has been supporting many of the experiments. The others here are working on the modeling and theory. So George Thomas, Sasha Strelnikov, and Luka Magatsu. And we have had a lot of collaboration with, for instance, Sergei Kubatkin at Chalmers University, and Xuntao Wu, Andrew Cleland at the University of Chicago, and as I mentioned, Oleg and Sergei, and Franco Nori, and then this Johnson Junction, this radiation detection we did together with Charles Marcus, and then theoretically modeled it with Alfredo Levi-Yeyat. Thank you.
Thank you, Professor Pekola, for the very beautiful talk. Questions, comments, please. Let me start the discussion by asking you about almost 1 meter quantum objects, about quantum transmission line resonators. So
Yeah.
In the first part of your talk, you were mostly speaking about mesoscopic objects.
Yes.
Can we say that these are microscopic size quantum objects, and what's the difference between them?
Yeah. So of course the frequency is much lower in this case when you have a 1 meter resonator. So that was just to. I mean, this is not our main objective to make them so big. It was just to demonstrate this kind of recoveries in this physical system. So let's say all this. I can say that some of the measurements were done on semi-microscopic systems. So this first heat transport experiment that I showed, where we had this quantum heat valve, that was also within like 5 centimeters photonic heat transport from one end to the other. So basically by dimensions we tune the frequency of the system. That's all.
Yes, Andrei, please.
Thank you for an interesting talk. When I saw your scheme for quantum heat valve, I was thinking that it looks very similar to heat engine scheme, and Are there some ideas for quantum heat engines, and what could be then efficiency of this?
Absolutely. So, in fact, to make a heat engine as such is a little bit tough from the point of view of demonstrating it. Where does the work go in an engine? So refrigerator is somehow simpler. So the design that I showed, if one just makes one of the resonators shorter, it's already an auto refrigerator in fact. And there you get the efficiency which is given by this 1 minus ratio of the frequency. So it's possible. So making a refrigerator in principle is very straightforward out of this design. Engines also, it's just actually one needs still to think a little bit. Where is the bucket? Where does the work go?
Like current, then so transform to current.
Absolutely. Yeah, one should measure tiny currents. Yes, sure. Or charge some capacitor or whatever.
I see. Thank you.
You're welcome.
Andrei Lvovich, did you want to ask? No? Then Gleb, please. Gleb Skorobogatyko.
Okay. Just maybe about general physics. It's interesting whether there can exist or not certain very general relation which bound the quantum detection in this situation. Meaning, you mentioned that on one hand you can treat qubit as a tool, as a switcher to detect photons. On the other hand, it can be the smallest possible thermometer.
Yeah.
And is it possible that these two features can spoil the effect of each other? It's like Niels Bohr complementarity principle, and you cannot see quantum. So you always should pay the price.
Absolutely, yeah. So I mean, as soon as you couple it, you make it decohere. So I think this is one of the interesting directions in whole this business, is that you start to come to these questions of how the measurement, how the coupling to the environment influences your system. It's kind of going back to the collapse and Niels Bohr and whatever. So we have the possibility to choose how strongly we couple these detectors there. So it's a nice way of testing these principles. But of course, in the simplest possible way, it simply the system relaxes or dephases due to this increased coupling to the bath, which is like a measurement itself. But then you can also ask a question: is there some extra thing when you probe? For example, when you connect this calorimeter, it already kills the coherence slowly, maybe. But is there an extra effect when you start to measure the temperature of this electron system there? I don't have clear answers, but it's something that we have now kind of pieces with which we can play with these fundamental questions, I think. I don't know if this was what you were interested in.
Yeah, I just thought about this, like when you detect photons, then spontaneous interaction with phonons can affect the levels of the the state of the qubit. On the other hand,
Yeah.
if you measure temperature with with the tool of qubit, then you should be able to somehow extract the signal from the qubit. So probably you should average over all processes of emission and absorption of photons, and then it involves a sort of averaging in temperature measurement. So in this sense, is kind of price.
It is.
Always exists.
Yeah.
It's interesting to derive a sort of simple and general relation which connect, for example, characteristic energies of phonons and the resolutions, meaning photon measurement resolution, phonon measurement resolution, something like that.
Absolutely. And then, of course, one of the key features is that superconducting qubits are so well characterized, and you can engineer them so well these days that you really play these games to try to extract and to understand some of these fundamental issues with them. As I said, it was not possible 30 years ago. It was not possible probably even 10 years ago, but now it starts to be on the level, thanks to the huge investments on the superconducting quantum qubits, quantum computer, that things are so advanced that we can play with a lot. We can play with many, do a lot of games with them.
Thank you very much for a very interesting talk.
Thank you. Thank you.
Other questions? Then probably that's all for today. Thank you, Professor Pekola. Thank you so much for the very nice talk and discussion. Thanks to all. See you next time. See you in 2 weeks.
Thank you. Thank you for listening. Bye-bye.
Bye-bye.
Bye-bye. Thank you.